I will begin with a word of prayer. So, Heavenly Father, we thank you for this time together to study your creation, and thank you for this class. Just ask that you guide our steps today, help us to glorify you what we do. And in your name I pray, Lord Jesus. Amen. Yes?
For 28, is the negative, on the dz dt, is the negative 13 supposed to be negative 13x, not negative 13? On here, is it supposed to be negative 13x?
Yes. Thank you. So problem 78, that would, there's a spurious extra z there, but it's supposed, the last equation is supposed to read x, y, z, not z, y, z. So, yeah. And that's a very significant difference, because with the z there, the matrix is symmetric, I think. But without that, I mean, it's not symmetric, but if you put an x there instead of the z, which is written, it becomes like much easier. Okay, so today I should talk to you guys a little bit about like, oh man, did I not bring my marker bag today? Well, that's annoying. Give me a second here, guys.
So you're not staying for the pie?
I know. All right, I'm back. Now with markers. So there's something called a difference equation, right? So like difference relations and recurrence relations have a lot in common. I don't have the full theory worked out for you today, unfortunately, guys, but like a typical example of a recurrence relation might be something like this. We have x sub, let's say, k plus 1 equal to a times x sub k, right? So here, the idea is you have some initial state, x naught, let's say, right? And then you multiply by a, you get x1, which is a x naught, right? And then you multiply by a again, and you get x2, which is a times x1, which is a times x naught, also known as a squared x naught, right? And this goes on, okay? And so then you go to like x3, which would be, after we work it out, you know, a cubed times x naught, and so forth and so on, right? Finally get to the, the kth state, which we can work out is going to be, you know, a to the power k times x naught, I think. Yeah. So there are all kinds of physical problems, engineering control problems that come up like this. So this is discussed, it's called discrete dynamical systems. And like section 5.6, your book has, you know, about 5 pages of discussion on it. And the mathematics here is very much what we've already done. So like, let's talk about it. So here I'm thinking of A as an n by n matrix, okay? So, and again, just to context here, I probably should, usually kind of bad form, I should put this title first, right? Discrete dynamical systems. So why do we say discrete? What's that word mean? So this is section 5.6 in lay. So this is, unfortunately, this is one thing I don't really have in my notes, in the sense of, like, I don't have the general theoretical backdrop for this much in the notes. There is an example at the start of my eigenvector chapter where I actually kind of study this for a specific matrix and a specific point. And I show you how different points get pushed around, you know, by a particular matrix, and how you can kind of see the eigendirections from that. So that is in my notes. But anyway. So the question here is, what can we say about this kth state vector if this is the situation, right? So, well, if A is diagonalizable, then what? Well, then we can write, how we can say A is equal to what? P inverse AP. If A was symmetric, that inverse can become the transpose of the basis matrix, but we don't know that for sure in general, right? And that's not true. I saw some of you scratching your heads. That's good. That should be a what? D for diagonal, right? Specifically, it is lambda 1, lambda 2, lambda n, right? The eigenvalues are what it diagonalizes to. And so, of course, we can take that equation and we can solve it for A, right? We can get A is equal to P D P inverse. And as we discussed yesterday, because Thursday doesn't exist to us, A to the power K is equal to P D to the K P inverse. Or explicitly, if you want, to be more explicit, V1 Vn, the eigenvectors, right? And then d to the power k is nothing more than like lambda 1 to the k, lambda 2 to the k, lambda n to the k times that same basis matrix inverted, right? So that gives us a stone-cold formula for the kth power of the matrix if we want to calculate it, for one thing, right? So one way you could approach this calculation would be just to, explicitly find that. Let's see here. So there's actually how we calculate a to the k if you want to. All right, but let's do the kind of calculation I did before. I'm going to try anyway. What happens? Oh, I don't know if this goes well. All right, give me guys about 3 minutes, and if it goes well, it goes well. If it doesn't, we'll bail, all right? So this right here, I can convert to eigencoordinates how? So if we let y equal to the inverse basis matrix times x, right? Then y in my other notation would be the coordinate vector of x with respect to the beta basis, which I'm taking to be an eigenbasis here. I'm assuming A is diagonalizable, right? So, all right. If I solve this for x, we get, beta times y, right? So, likewise, we can say x sub k is equal to beta times y sub k, right? We could take the difference equation, right? Well, I'm calling this a difference equation, recurrence relation if you prefer. There is an intimate link between difference equations and recurrence relations. You can go back and forth between those two formalisms. Maybe that's something you should see in discrete mathematics, not here though, yeah? So I need to talk to the discrete mathematics professors, find out if they do it in there or not. If they don't do it, maybe I'll come back here and do it another day. Yeah? But I don't know. I haven't taught Math 250, so I don't know. Yeah.
They do.
Oh, they do? Okay. Well, good. One less thing for me to do this semester. Woohoo! And the rest of you are like, phew, yes. One less thing to do in this course. Great. So, all Anyway, there is the state variables. You could either go in the Cartesian coordinate system we're starting with, or the eigen coordinate system, the y, all right? So then, if we plug those into up here, we get what? We get like beta times y sub, y sub k plus 1 equals to a times beta y sub k, right? Just making a substitution. Substituting x sub k plus 1 for my corresponding y sub k plus 1 times beta, right? We can do this. And then what do I do? How about multiply both sides by the inverse basis matrix, right? So this would tell me that I've got inverse basis matrix. Oh man. This would tell me that y k plus 1 equal to the inverse basis matrix times A times the basis matrix times y sub k. But what is that beta inverse? I mean, look up here, right? So this and this is the same, right? You ever seen that stupid meme with Pam from The Office? Apply it here. Okay. They're the same thing. So, sorry, that was redundant. Anyway, the point is that, these are literally the eigenvalues times the kth state vector, right? So if we look at y sub k plus 1, the jth element of it, right? That's equal to lambda j times y sub k, the jth element of that. So the reason for the double index is we're talking about a state vector, but we've got a whole sequence of them, right? So the kth vector in the sequence is the k index. The j is just like the component of that vector. But as you can see, in eigencoordinates, it's stupidly simple, right? To get to the next step, you just multiply by lambda, right? And so if you extrapolate this, we get, y to the y sub k is equal to, so the jth component of it is equal to lambda j to the kth power times y sub naught, the jth component of that. All right. So more to the point, if we had that y naught was equal to like c1 v1 plus c2 v2 plus da 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 plus cn vn, right? Because if you think about it for this problem, for any given matrix, the initial state vector we can write as a unique linear combination of the eigenvectors for the matrix, right? And so when we calculate the kth state vector, what do we got? Well, we have, nothing more than, let's see here, d to the power k times y naught, right? But what is that? It's like c1 d to the power k times v1 plus c2 d to the power k times v2. But you remember yesterday we worked out, because Thursday doesn't exist, yesterday we worked out that if you have an eigenvector for a matrix, it's also an eigenvector for the power of the matrix, right? But notice that the by construction here, well, anyway, what happens when you take? Oh man, I'm sorry, guys. Give me a second. Sorry, my brain skipped. Well, I want to say what this gives me is, that's not quite right. No, it's right, it's right. I'm sorry, guys. I'll get with eventually here. So C1 lambda 1 to the power k. Is that right? No. I'm sorry, guys. I should write the initial condition not in the eigencoordinates like this. That's what's confusing me. I need to put this as x naught. Sorry. Okay. And if I do that, I have to calculate slightly differently. So if that's x naught, what happens when we, calculate a to the power k on x naught? What happens with that? Because that's the kth state vector, right? So you get c1 a to the power k times v1, right? There we go. Now I feel better. A to the power k times v2. Now, we're assuming, what about the v's? We're assuming that they're eigenvectors with eigenvalues, what? Lambda 1, lambda 2, lambda n, right? So what happens when we take a to the power k times the eigenvector v1? We get what? So this is just c1 lambda 1 to the kth power v1, right? c2 lambda 2 to the kth power v2. Plus plus cn lambda n to the kth power vn. Do you guys know what I'm doing? I'm assuming here that a times vj is equal to lambda j vj, right? That's the assumption that this is an eigenbasis for the matrix A of the problem, which I'm assuming is diagonalizable. And as such, that calculation we went through last class, right? Lambda squared, a squared has the eigenvector v with value lambda squared. A cubed has the eigenvector v with eigenvalue lambda cubed if av is equal to lambda v, right? Still true here. And so then what? Like that's the general solution. And if you translate this into the eigencoordinates, what does it say? It says like basically yk is equal to, you can just make a column vector out of this, right? If this is the vector xk, right, written with respect to the beta basis, what's the coordinates? The coordinates are the coefficients of the basis, right? Which in this context are c1 lambda 1 to the k, c2 lambda 2 to the k, cn lambda n to the k. See, that's exactly the coordinate vector, if you will, of xk with respect to the eigenbasis here. Okay, so now that we've got this theoretical backdrop, can you analyze what happens with the discrete dynamical system? So like what's the behavior, right? What's the limit as k goes to infinity, right, of x sub k? What happens there? Can we discuss that? Right? Because certainly you could go back, right? And well, I mean, there's no need to go back. The formula is right here. Here's the formula for it in Cartesian coordinates right there. Let me underline it in red. So what happens with this? What happens with this formula here as k goes to infinity? Well, here's one thing that happens. If any of these coefficients are non-zero, right, and they're paired with an eigenvalue which has magnitude greater than 1, well, that goes to infinity, right? So if the eigenvalue is larger than 1, it blows up. Boom, you know? And if it's negative, then it's like it's getting really, really positive, then really, really negative, and just oscillating madly as k goes to infinity. So the only way that this could settle down to something finite, right, for there to be a quote-unquote steady state solution. What would a steady state solution look like? Steady state solution would be something like, you know, basically x star equals to, you know, x star. Like if I had that, that would be what we would call a steady state solution here, right? In other words, it's a state that once your dynamical system gets to, when you go to the next step, you're just back where you started again, right? This is a stable solution to the recurrence relation here. So like if there was such a thing, that would be what? An eigenvector with eigenvalue, what? 1, right? This would make x star an eigenvector with eigenvalue 1. So if you've got one of those, you've got a stable state, right? What else can happen though? There's really kind of 2 basic cases, maybe 3. One case that could happen is if you've got even one of these eigenvalues which has magnitude larger than 1, it blows up, right? Because as you take a number larger than 1 and you raise it to an infinite power, it gets really, really big. On the other hand, if the magnitude of all the eigenvalues is less than 1, right, then as k goes to infinity, they all do what? They all go to 0, right? And so it wouldn't even matter what the initial state was. You know that they're all going to get sucked into the 0 state, right? So that would make the origin what's called an attractor. If there is all the eigenvalues are greater than 1, right? Then I feel like they have to be positive. I don't know how to think about negative eigenvalues. It's definitely unstable. If you have any negative eigenvalue, like it makes it kind of like, it doesn't stay at the origin, it just kind of oscillates around the origin. So I'm not sure what to call that, but if all the eigenvalues are positive and larger than 1, definitely the origin's a repeller, right? The solutions will flow away from the origin for a large time, for sure. I'm thinking of time occurring between the states. So oftentimes, like think about it as being 1 second as a useful thing, but the discrete time step doesn't have to be 1 second, right? It could be whatever. Like these states could be related by a nanosecond for all I know, right? Or I don't know, what are the states in a computer, modern computer? What we're talking, what gigahertz speeds? What we're talking about between cycles? What's 1 over a gigahertz? That's the time. It's a lot. Well, it's not a lot. It's a very little. Like 1 over. So I think we're talking about like a nanosecond, right? Or something like that, on the order of nanoseconds. Anyway, so my point was, if all of the eigenvalues are, have magnitude less than 1, then as k goes to infinity, they all go to 0. The solution attracts to 0. If, on the other hand, you do have an eigenvalue which is equal to 1, right, then that is a stable state of solution. And I think typically, for a lot of systems, that will be what the solution tends to for a long time. It has to, right, if it does have a stable outcome. But anyway, more and consistent language about all this is given in section 5.6. Do you guys see the relation to do you guys see the relation to the differential equation? Like doesn't this look almost like, this is very reminiscent of the solution to what? If we have dx dt equals to ax, so this is section 5.7 in your book, right? Which I've already been covering multiple days. Gets kind of more my wheelhouse is continuous things. I'm not very good at the discrete stuff. I don't know as much about it. But anyway, so dx dt equals ax, that's a differential equation, right, with the same matrix. If it's also an n by n, what's the solution? Well, we worked this out, right? The solution would be x is equal to like c1 e to the lambda 1t plus times v1, right? Da 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 plus Cn e to the lambda n t times Vn. Notice how similar these solutions are, and yet quite different. Yeah. What's the relation between, say, the recurrence relation and the differential equation? Let me show you one way you can think about it. So one way you can think about it is that you can think about this as like a change in x over a change in t is equal to ax, right? And if you do that, and we say change in x is equal to, let's say, xk plus 1 minus xk, then I get xk plus 1 minus xk is equal to a x, let's say k, times delta t. But, you know, let's say delta t equals to 1 for the sake of discussion here. Then all of a sudden you've got what? You've got xk plus 1 is equal to a plus the identity times x sub k. So there ought to be like a direct relation between this recurrence relation and the differential equation, in the sense that this solution to the differential equation should give you some sort of like continuous extrapolation of this particular difference equation. Not the same matrix, but closely related. And then I suppose you could ask the question, okay, well, can we say anything about the eigenvalue of a matrix and a matrix plus the identity matrix? What do you guys think? This is a question I'm asking for the first time for myself. Let's see if we can answer it together. If AV equals to lambda V, what then about A plus I? What can we say about it? What do you guys think? Is there any kind of relation between the eigenvalues of a matrix and the eigenvalues of a matrix plus the identity? I have been so conditioned to assume that there's no pattern, right, guys? Because most things it doesn't go well. If you change the matrix even a smidgen, it changes the eigenvalues. It's really annoying. Finding eigenvalues is what's called an ill-conditioned problem. Like, it's not numerically nice. So you got to be wary. But I think this works out really nice. What happens if we multiply a plus I times v? We do what? We got AV plus IV. That's the identity matrix, right? But AV was what? Lambda V. And that's V. So, dude, check that out. So apparently, V is an eigenvector for A plus I with eigenvalue what? Lambda plus 1, apparently, right? So if I want to directly compare the discrete and the continuous solution, I should really look at like x equal to what? Like c1 e to the lambda 1 plus 1, right? So maybe I should compare that versus, I don't want to write it again. Fine. xk equal to c. It doesn't have to be the same c1 through cn, so let me be a little bit cagey about that and write b1 lambda 1 to the power k v1. I really don't know, guys. I'm just writing this out here. What is the relation between these? No idea. But I feel like they should be interlinked in some way or another. Oh, well, Anyway, I'm just going to leave that as an open question. I don't know how to answer it or even to entertain the question really, but sorry, every once in a while I play in here. Hopefully not too much, but there's more time to play in Math 321, so let's leave it for there. You're like, yay. Let's see here. So you guys have questions about your homework? We do have time, so. Listen, there are a couple of numerical examples in the book for this. For the most part, we're interested in like 2x2 examples for this kind of thing, right? To do 3x3 examples, to actually sort of probe these numerically, which is probably more what we should be doing. You really want to get out MATLAB, you know, put your specific matrix in there, throw some points at it, and just raise it to a power. Like, just actually carry this out for your specific matrix and your specific like initial condition. See where it goes. See what happens. Look for patterns. You got to be able to see eigenvectors in that. So, no questions? No? All right. Well, yeah.
Is there a test next Friday?
There is a test next Friday. Yes. I mean, sure. Why not? Yeah. I mean, if it's in the schedule, it's there. I'm planning for that. All right. Well, I don't know if this has been helpful or not, but I tried. Let me solve yet another complex eigenvalue problem. Let's see here. So, all right, book, don't let me down this time. All right, here we go. Example 1, I guess. Here we have A equals 2, minus 2, minus 2.5, 10, and minus 2 with initial position 3, 3. And we're supposed to solve this using the complex eigenvectors, eigenvalues. This is the differential equation which occurs from a particular RC circuit, actually RLC circuit, I should say, that's shown on page 360. All right. So page 360 of lay. This is, and so anyway, let's get to it. So we're trying to solve dx dt equals to ax, which again has the significance of being arising from an RLC circuit. Okay, so we start by finding the eigenvalues. I need determinant of a minus lambda I, which is the determinant of minus 2 minus lambda minus 2.5 times, there's a 10 here, and minus 2 minus lambda. So that gives us a lambda plus 2 quantity squared. Minus and minus gives me plus. 2.5 times 10 is 25, so plus 25. Oh, that's beautiful because that's already the difference of squares if you use your imagination. See, that's lambda plus 2 plus 5i, lambda plus 2 minus 5i. Right? So in short, we can put lambda equals to minus 2 plus or minus 5i. These are my eigenvalues, complex eigenvalues. Would you guys like me to pick the plus or the minus to find the eigenvectors for? The minus? Minus it is. So let's look at lambda equals to minus 2 minus 5i for the sake of finding our specific complex eigenvector. So here we go. We have a minus lambda I times, let's say, u equal to 0. Now that specifically is the 2's, they be canceling, and so we get 5i here, minus 2.5, 10, and apparently 5i. All right. And then my disposable variables, I guess I should have called this u1. So u and v, as is my custom. Now, if we did this right, these should be the same equation, right? So just as a double check on the correctness of the mathematics here, notice that if we multiply the first equation by minus 2, minus 2i, minus 2i times 5i, what's it give you? It gives us minus 10i squared, which is 10, right? And what's minus 2i times minus 2.5? It is 5i, right? So this is not necessary for the calculation, but it is a redundancy check, right? If I did this right, it must be that the two equations are the same equation. If the two equations are not the same equation, that means that our eigenvalue is not really an eigenvalue, because you're only going to get the 0 solution if you solve it correctly. Now, if you want to maintain a state of plausible deniability, just don't do this and just pick one of them and use it to solve. You can always do that, but you'd be wrong if this didn't work out. I personally like number 2. So that gives me 10u plus 5iv equals to 0, which we can solve for. V is equal to 10u over 5i, right? And that gives me a 2 over I times u is equal to v. So if we do what? Like if we let u equals to I, that's kind of nice, right? If I let u equal to I, then my v is 2. And so my complex eigenvector is I and 2, which I can rewrite as 0, 2 plus I times 1, 0. So folks, this is the A, and this is the B. So here A is the real part of U1, B is the imaginary part of U1. All right? And as we derived the other day, once we have that, we can write down the solution. So the solution, well, all right, there's different ways we could go here, guys. So here's the unexciting way we could go, is we could go back to my general solution, we could just write it out, and then we could pick constants which make this the initial condition. That seems like a lot of work. Let me show you an easier, like, silly, stupid way. So generically speaking, z equals to e to the lambda t times u1. This is a complex solution. Complex solution to dx dt equals to ax, right? How can you make this complex solution have initial condition 3, 3? Oh man, that doesn't help, does it? Oh, never mind, guys. I had dreams of not calculating, but I think I'm stuck with it. Ah, life without a shirt. It's no life. Yeah. Well, this is kind of better. I don't know how Dr. Sperano lives. Let's see here. He has his ways. Let's see here. So, fine, I'm just going to accept my medicine here. So we have x is C1, and basically the way it works is C1, the real part of that Z solution, right? Plus C2 times the imaginary part of that solution. And we worked those out the other day, so we don't need to do that again. I'm just going to quote my calculation from the other day, which is that it works out to, so here, lambda is equal to what? My lambda was -2 minus 5i. So this makes the alpha -2 and the beta equals to -5. All right, so we've got C1. Oh, let me factor the, goodness gracious, e to the -2t out. And then I've got myself a cosine of -5t a minus the sine of -5t b plus C2 e to the -2t times the sine of -5t a plus the cosine of -5t b. So again, I'm referencing the calculation I did like 2 classes ago. All right. And so what does that actually give me? Remember, sine is odd, cosine's even, right? So we've got like C1 e to the -2t, and let me just try to work it out. What is a? A was what? A was 0, 2, right? So I get a 2 cosine 5t in the second component. And that's from the cosine term. The sine, notice the minus and the minus pulls out, so we just get a plus from the second term there. And b was 1, 0. So in short, I get a sine 5t up here. And then I get plus C2 e to the -2t. And let's work that out. So the minus pulls out. We have a minus a for the, so like -2. We get a -2 sine 5t down here. And the cosine is even. It eats the minus. And the b was 1, 0. So I get a cosine 5t up here. All right. Now what? Have we used the initial condition yet? We have not, right? So x of 0 is equal to what? 3, 3. So here's the deal, guys. If you're not given an initial condition, the general answer involves 2 constants, right? Those 2 constants reflect your ability to choose different initial conditions. But if initial conditions are given, then the constants go away and you have a specific and unique solution to the problem, which we will have here. So if I plug time 0 into this, what happens? We get what? C1 e to the 0, also known as 1. And this just becomes 1, 2. My bad, 0, 2. Plus C2 times what? 1, 0. Oh, this is super nice. Check that out, yo. So that's C2 and 2C1. So apparently we can put C2 equal to 3 and C1 equal to 3/2. Go back, stick those in here, and we'll get like x1 is equal to, you know, like 3/2 sine 5t. It's supposed to be a sine 5t plus 3 cosine 5t all times e to the -2t, and x2 is like 3 cos 5t minus 6 sine 5t e to the -2t. There you go. That's the honest to goodness solution to this complex differential equation. And what would the solutions look like if you were to plot them? If this is x1, this is x2, right? You're starting out at 3, 3, right? What happens to this solution? As t goes to infinity, it does what? Goes to 0. So this thing, if we could do it, it would be something like that. And I really don't know how many big loops it makes. I'm just totally speculating. There is something called p-plane. P-plane in MATLAB. You can actually visualize the direction field to a differential equation and like directly plot solutions. It's pretty cool, even when you can't solve them. Anyway, maybe we'll look at that some other day. I shut up. By the way,